So hi everyone. A little bit of pressure because yeah. So today I'm going to present the Arborescent Garbage Collection, a dynamic graph approach to immediate cycle collection. So this is joint work with Frédéric Lahaie-Bertrand, Olivier Melançon, Marc, Feeley, and Stefan Monnier. It was really a pleasure to work with them on this new garbage collection algorithm. So our problem for today is collecting cycles immediately. So what do we mean by immediately? We mean that the garbage is collected as soon, actually before any other operation by the mutator. So in other words, it's done before we go back to language space. And if we look at commonly existing techniques, there is tracing, which can collect cycles, but do it in a deferred way. And there is reference counting that can collect garbage immediately in our sense, but doesn't collect cyclic structures. So why do we want to collect cycles immediately? There's a couple applications that are interesting, but most of them revolve around finalizers. So doing something when a certain part of memory is removed. And for example, if we had the ability to collect all garbage immediately, we could interpolate with a garbage collector with, for example, C++ or Rust destructors. So our approach here consists of first of all modeling the heap as a reference graph. So here the graph that we see, each node represents an object in the heap, and links between them mean that they have a pointer pointing to it. And what we will do is we will embed a spanning forest within this this reference graph. So, and if we think about it, the problem of garbage collection can be seen as finding a spanning forest starting from the roots, and all nodes that are part of this spanning forest are actually reachable, and we can collect all of the other nodes. So here in the graphs that I show, each edges in black here will be part of a spanning forest, and the one in gray will be part of the reference graph. And our approach will be to maintain the spanning forest during the execution of the program. So while the program executes, we will remove and add references. This will correspond to changing the graph. And our goal would be to rebuild this spanning forest while we are executing. So now let's go over some definitions. So here we will model the roots or the uncollectible nodes as yellow in the graph here. If we have a black edge, we will call nodes between them as having a parent and child relationship. So for example, D here would be the parent of G, and G would be the child of D. And we will add another relationship, which we will call the co-parent and co-child relationship, which is relationships between edges that are not part of the spanning forest. So for example, here B would be the co-parent of G, and G would be the co-child of B. So our work is inspired from ES trees. So I won't pronounce the word here because I'm not exactly sure how to pronounce it. So I'll say ES trees for the rest of the presentation. But ES trees are a data structure that are that is used to maintain a minimal spanning forest. And it has been developed in the field of dynamic graph theory. And it uses a notion of rank to keep this distance. So at each moment in time, it keeps a rank for each node, and it changes it and recomputes the rank as the graph changes. And we will see how we will use this notion of rank to create our algorithm. And also, in the case of ES trees, ranks are strictly monotone, so always increasing in increments of 1. However, in the case of garbage collection, we don't need a minimal spanning forest. We just need a spanning forest. And as long as we have one, we know that all nodes within the spanning forest are actually reachable. So we'll distance ourselves a little bit from even ES trees. And our goal will only be to maintain a spanning forest. We will also relax the notion of ranks to be increasing, but not necessarily of increments of 1. And we see also that in our case, ranks are will mostly be used for optimizations. So here is an example of a valid kind of rank structure in our algorithm. And we can see that along the spanning forest, all nodes are increasing, but not necessarily of increments of 1. So now we have all the background knowledge to kind of see a little bit what our new algorithm is. So our goal here is we have this reference graph, and we want to maintain the spanning forest over the over these operations. So the addition of an edge, the removal of an edge that is either inside or outside the spanning forest. And 2 of those operations are really easy to do, and one of them is really hard. So maybe you can already guess which one is which. So we'll start with the addition of an edge. So let's start, let's say we want to add an edge between those 2 nodes here. What we can do is simply add an edge that is not part of the spanning tree, and doing so just works. So we don't need to do additional work, and the reference is thus added, and it's still a spanning tree. If we remove an edge, let's say we remove an edge that is not part of the spanning tree here, again, we can simply just remove it, and it's going to still be a spanning forest. The hard part is if we remove an edge that is part of the spanning tree. So let's say we want to remove the edge that is here. If we do it, we will use a 3-part algorithm that can, we will use a 3-part algorithm to fix the spanning forest. So the first step is to drop, is a drop phase. So the drop phase is a bit the phase that tries to mitigate how much damage we get from removing this edge. And what we will do, we will start from the initial, we will start from the node that is pointed by the edge that we remove. And we will do a BFS from there to mark all those nodes as falling. Okay? And at the same time, we will mark all nodes from these falling nodes, all co-parents from these falling nodes as anchors. So I'll play a little animation, and you'll see this ongoing. So here we have done the drop phase. We have marked all nodes as falling. And at the same time, we have marked 2 anchors. And we will see that the anchors play an important role later on to actually rebuild the spanning forest. So now we can move to the catch phase. So in the catch phase, we will start from the anchors, and we will try to fix the spanning forest and mark all falling nodes that we can still reach. So all nodes that are still reachable. And I think I'll just play the animation. It a bit explain itself. So here, as we can see, we can find all nodes that are still reachable from these anchors. And this way we can know which falling node is still reachable from roots. And as a last step, we will perform the collection of all nodes that are still falling. So here we will simply collect the node on top. And as we can see, this is still a spanning forest. So now the question is, can we use this in practice as such? And as some of you may already see, we cannot use it like this. And the reason is it's about 3 orders of magnitude slower than our baseline, because it's super slow to perform all of these operations on each modification of the heap. And a bit of an intuition behind it is we're tracing pretty much every time a pointer gets modified. So the question is, how can we make it faster? So we have a couple of optimizations. So the first one is called adoption. So an adoption can prevent a node, it's done during the drop phase and can prevent a node from falling if it has a co-parent that has a smaller rank than itself. So again, this is the same graph as we had before, and I'll just play the animation. And as you can see here, this node is about to fall, and this node here is a co-parent with a smaller rank than itself. So we know that we can just modify the spanning tree in place and kind of catch it early on. In this case, it didn't save a lot of nodes from falling, but we could imagine that the 3 dots here are a big subgraph that we would have needed to mark in the falling phase, but now it was prevented by the adoption. And we also know that we cannot form a cycle by doing so because of our rank invariant, so that ranks are always increasing. The second optimization is called re-ranking. So in our case here, we have a new graph. So imagine that the 3 dots here are again a huge subgraph that we really, really don't want to traverse. And the edge in red here is the edge that we want to remove. So if we try to drop this node, we really, really wish that this node here had just a rank a little bit smaller. The reason being that it could adopt it and don't have to traverse the big subgraph. So what we can actually do is just reduce the rank of a potential co-parent so that we don't need to traverse this subgraph. So this is what we will do. We will modify the rank of the nodes here in blue so that this co-parent can now adopt the falling node. And doing so, we can modify in place the spanning tree again to create a valid spanning tree. However, this optimization is a little bit risky because we need to traverse parents going up. And we need to we can only stop if we find a route or we remove enough gaps between the edges to actually increase the co-parent enough. Another scenario that can happen is when we go up, we can actually traverse back to a falling node, and if this happens, we know that we cannot use this co-parent as a valid adopter. And because of this kind of risky move, we only perform re-ranking on the first few nodes each time we do a drop. The third optimization is the choice of the initial rank. So when creating a new object, we can choose its rank. So for example, here we created a new node and we chose to give it a rank of 0. So in our case, we initialize rank with a decreasing global counter. And the reason is that when we create a new object this way, we know that this new node can adopt every node that already exists in the graph. So if we create a bottom-down structure, we can simply add new node really easily without having to do extra work. So as you probably know, the devil lies in the details. There's a few things that we didn't mention about implementation, such as how do we keep the co-parent co-child relationship in memory while we perform all of these operations. So the answer lies in this picture here. We actually embed the co-parent co-child relationship as a linked list, and we use kind of a clever trick if I can say so, to not have to use any additional external memory allocation. So everything is done as metadata that is added to our object. And also, as you can see, the cost of using our garbage collector algorithm is 2 times of the object plus 4. And there is a whole section about implementation in the paper if you're interested into how we actually implement this algorithm and keep all of this information about parents and co-parents. Now we can talk about benchmarks. So we used Ribbit as our benchmark, which is a scheme implementation. Ribbit is a little bit a torture test for this garbage collector, because almost all operations in Ribbit are memory operations. For example, in Ribbit, the stack is a linked list. So it's very costly to do operations. Ribbit supports multiple garbage collectors. So in this case, we compared it against the mark and sweep implementation of the garbage collector. So here are the benchmarks. On the y-axis, we can see the execution time in contrast with the mark and sweep implementation. And on the x-axis, we can see all the different benchmarks used. So we see that we have about a 4.5 times slowdown compared to mark and sweep, which is impressive. Impressive, I don't know, which is better than previous work. So what is the future work? There's a couple directions that we can go from here. One direction is to have more optimization to make this algorithm faster. So for example, using better heuristics. Another idea is to use language information, such as we know that certain structures cannot contain cyclic references, so we don't need to actually use all of this logic, and we could use a reference counter, for example, for part of the reference graph. Another direction could be to implement it in real-world scenarios, such as interoperability with C++ or Rust destructors. And finally, another direction could be to look at other dynamic tree structures in dynamic graphs to see if there is other structures that can be applied to the garbage collection problem. So in conclusion, the arborescent garbage collector collects cyclic structures immediately by embedding a spanning for us into the reference graph. We add a weak notion of rank on objects, allowing the adoption and re-rank optimization. Our technique is about 4.5 slower compared to the mark and sweep implementation, where previous work was prohibitive and unusable synchronously. And we believe that immediate collection of all garbage can enable application requiring timely reclamation of resources. So thank you very much. And
oh, we have maybe more questions than minutes. So maybe if we start at the back and come forwards again.
Yeah, thanks a lot for a very interesting talk and paper. So question I have is, yeah, it's slower, but can you give a breakdown or intuition where is this time spent? As in, like, you have many different, kind of, let's say, paths in your algorithm. Can you kind of tell us which part takes the most wall time?
yeah, it's a really good question. Actually, I have a hidden slide on this. So if we look at the backup slides here, we have another graph that shows a little bit where time is spent on each kind of phase of the algorithm. So we can see that in most benchmarks, it's pretty evenly distributed for the first three, but there's a few ones where we have kind of outsiders. And for the Boyer one, we believe that it's because when we collect garbage, we actually have to remove all cofriends, and in this case, there's a lot of cofriends, and yeah. So anyway, that's it.
Thank you. Did you consider parallel mutators, and also did you consider batching?
Sorry, can you repeat?
Did you consider parallel mutators, and also did you consider batching of this processing, addition and removals?
Yeah, we didn't consider parallel implementations, and I don't see a straightforward way to implement it in a parallel way. There probably is, but it would be a future work. Yeah.
Okay, maybe there's the last question.
Yeah, so you said there was previous work that was a lot worse, but can you say a few words about what it is, and is it yours? I don't know. And just a simple, short question also. The Evan-Shiloach tree, it was minimal in something, and you were not. In what was it minimal?
Okay, so when I talk about previous work is that the previous work that exists was too prohibitive to be used synchronously. They had to use other, use it in a asynchronous fashion, because otherwise you would traverse your heap multiple times during the execution of the program. I actually also have a backup slide a little bit on the previous work here. And your other question about ES trees. So ES trees is a construct in dynamic graph theory, and its goal is only to keep the minimal distance at each moment from given roots. So its goal is not garbage collection. Its goal is really just to have to know the minimal distance from roots. But in the case of garbage collection, we actually don't need this information, so we can relax this notion of distance, let's say.
Okay, well, I think we need to take the coffee break now, but I'm sure you'll be here during the break and able to maybe expand on any remaining questions that people have.
Yeah, for sure. I'll stay here if you have questions.
Great. Well, let's thank the speaker again.
Thank you very much.
Yeah, I think we're resuming after the break at 3:40.